My name is Enrique, Dr. Enrique del Castillo. I'm a lecturer at the University of Auckland. Most of my research is also related to concrete structures and how concrete structures behave in seismic environments such as New Zealand. But I also do some work on sustainability of concrete, bridges, and various things. Envirocon contacted me a few months ago. They are designing their retaining walls based on mechanic principles, and these get often challenged by peer reviewers, by engineers, or by councils. So they needed experimental proof that their calculations based on the mechanical principles of retaining walls were accurate.
I'm a structural engineer, chartered professional engineer in New Zealand as well as in Australia. I play the role of a technical consultant, essentially providing technical support as required. And in this case, I think the whole team is very privileged to have someone like Dr. Enrique to be able to provide his input into the entire scope. And I do find that having him on board is a really good learning curve because with him I'm able to bounce off quite a fair bit of really good ideas in terms of trying to make the testing as robust and as conclusive as possible. And the whole intent of having the test, if I've not mentioned it previously, is really to eliminate assumptions and also judgment in it, because ultimately the compliance pathway towards New Zealand Building Code predominantly by structural engineers like myself will be using B1, VM4, and within that part of the building code, I think there is a very strong emphasis in terms of the performance of the wall under static condition as well as under earthquake condition. So in a nutshell, what we are looking at is, for a wall, we are looking at global stability as well as internal stability. So the main thing that we are trying to capture out from this test is to make sure that internal stability is being addressed and is being properly understood, and at the same time look at how the overall wall system performs under a global condition, assuming we are having really good ground.
So the tests were carried out at the University of Auckland in the Structures Test Hall in Newmarket. We have a quite big, strong wall on a strong floor in there. They can take up to 2,500 kilonewtons. So the load that we were going to apply in the wall is minimal. We built the wall directly on top of the strong floor. We didn't add any grouting or any post-tensioning systems. Here we have the testing setup with the computer recording all the data, the jacks that were used to apply the load. And in the back, we use a square hollow section to connect all the blocks together, stiffen the wall in the longitudinal direction, and make sure that we had a composite action of the whole wall instead of the blocks moving independently of each other in the long direction. And then we pushed the wall against the strong wall with a hydraulic jack. We included a load cell to record the load, and then we measured also the displacement of the wall at 3 points, at the top, in the middle, and at the bottom row of blocks. We observed that the two walls, the thin wall and the thick wall, reacted differently to the load. In the thin wall, we observed that each row of blocks rotated with respect to the row of blocks just below. So we had top block rotating, then middle rotating, and then bottom rotating, which creates 3 gaps, 3 cracks, and 3 stiffnesses in the force displacement graph. For the thick wall, what we observed is that the whole wall was behaving as a rigid body, so the whole wall was rotating, creating a big gap at the bottom.
This is a very good representation of how the wall actually behaves, because you're looking at a very conventional plot of load versus displacement. And well, I guess displacement is not really the main criteria in this particular context, isn't it? It's more of a case of the amount of load that the wall can actually sustain to maintain its structural stability. And what I can also see from here is the whole system, well, self-centered itself, i.e. in other words, after the load is being applied and being withdrawn, it managed to get back to its original position, which suggests that that's good.
It even bounced back, you see? Oh, sorry.
Oh, right, so, okay.
So it bounced back and then back to zero.
Wow. So the whole test becomes even more interesting when we are looking at a double thick wall, like what we can see on the chart over here, in which the target load given or rather calculated per theory is in the region of 35 kilonewton ish, and what comes out from the chart over here is literally spot on, and a hint higher, which is good, and that is normally what is expected from tests, because tests will normally give us result that is somewhat better. But what is really interesting about this result that we see over here is it's not too far off, it is within CUI, and it is really reassuring for structural engineers like myself. I can't emphasize it anymore. The simple reason being, within the New Zealand Building Code framework, we have acceptable solution and we have the verification method. And within verification method, we have to comply to the necessary material standard, such as NZS 3101 for concrete, NZS 3404 for steel, and the list goes on. And there would then be a set of standards, which is AS/NZS 1170 series, which dictates what we do in terms of loading. And what is more important is the fact that MBIE and NZGS has published 6 modules or 7 modules, can't remember, in terms of what to do for retaining wall design under earthquake condition. So as a structural engineer and geotechnical engineer, I think it's important for us to make sure that we comply to every aspect of the building code so that the design that we produce is safe.